This video is the first in a series of videos where I talk about anti-dysrhythmics, which are medications that basically correct the way electricity is flowing through the heart. Electricity is supposed to flow through the heart in a very specific way in order for the muscle to contract properly and to have the correct amount of cardiac output. So when you have a dysrhythmia, you have an electrical problem. And because the heart muscle responds to electricity, an electrical problem quickly becomes a mechanical problem. So then you could possibly have decreased cardiac output, low blood pressure, poor perfusion. So that's why we care so much about dysrhythmias, because the electricity problem causes a contraction problem, and that's going to lead to perhaps a cardiac output problem. So to understand the different classes of anti-dysrhythmic meds, we have to understand how electricity flows through the heart and how the cells work, and then we can understand the medication classes better. So there's two kinds of cells in the heart. There's pacemakers, and pacemakers generate electricity and carry electricity. So they can start an electrical impulse, and they can carry the electrical impulse along between the cells. Myocytes are only supposed to carry electricity. They aren't supposed to generate, but they do have the ability to generate electricity. And that's where some of the dysrhythmic problems come from. Myocytes starting an electrical impulse when they're not supposed to. But what they are supposed to do in a heart with electrical function that's working properly is they're just supposed to carry, but they can generate too. So these cells are a little bit different. Ions move in and out of them a little bit differently. And like I said, we have to understand the ion movements in order to understand the different classes of meds, because the anti-dysrhythmics are classed according to what they do to the ions and what they do to the sympathetic nervous system too. Okay, so to understand how ions move in and out of the pacemaker cells and the myocyte cells, we have to understand two things about ions. The first thing is that they move according to a concentration gradient, and that's the symbol for concentration. All that means is that ions like to go where there's less of them. So they like to move from where there's a lot of them to a little of them. If you have, let's take this last cell in the row here, just as an example. If this cell was absolutely surrounded by calcium, just a very high concentration of calcium outside the cell, and not as much as a concentration of calcium inside the cell, these calciums are very motivated to get inside the cell. Ions move according to a concentration gradient. They like to go from where there's a lot to a little. The other way that ions move is according to an electrical gradient. So I'm going to erase this last cell here and draw out an electrical gradient. So I'm just filling in this last cell to illustrate these points. Let's say on the outside of the cell, I had a lot of positive ions. A lot of positive ions. And they could be any positive ion, but they're just all positive. And on the inside, I had negative ions. And maybe there's an equal amount, or very close to an equal amount. But regardless, these positive ions are very motivated to get inside to where there is a negative charge. So we'll say positives love negatives. And of course, negatives love positives. And the opposite is true too. If you have a cell that's very positive on the inside, so I'm going to change the inside to positive, that means that the positive ions on the outside do not want to go in. They are repelled. They do not want to enter that cell because it's already positive on the inside. They don't like moving that way. They want to move towards a negative charge. That's what positive charges want to do. Okay, knowing that, we can understand how ions are going to move through these cells. So in the first row here, I have a pacemaker cell, and it's all the same pacemaker cell. So this is all the same cell, but I'm just drawing out what happens at different steps of the action potential. At the bottom of the screen, I have the same myocyte cell, but I'm just drawing out what happens. So let's start with the pacemaker cell. How do ions move in and out to generate electricity? Well, pacemaker cells, we actually start at what's called phase 4. And in phase 4, we have the cell sitting there, and sodium is slowly leaking into the cell. And notice these sodiums have a positive charge. So as the sodiums are leaking in, they're actually making the inside of the cell a little bit less negative. It starts out as pretty negative, but as the sodiums are going in, it doesn't make the inside positive, but it makes it a little bit less negative. And once that cell reaches a certain level, and it's actually minus 40 millivolts, calcium channels open. So it's the sodium going in and making the inside of the cell a little bit less negative that causes calcium channels to open. And now I'm on phase 0. Phase 0 starts when calcium channels open. So I still have that sodium inside the cell. The inside of the cell is still negative. And now I have calcium absolutely rushing in. And that calcium is motivated to go in because the inside of the cell is negative. So, of course, a positive calcium is going to be attracted to that. And also because there's a lot of calciums outside the cell. So the calciums want to get away from each other. They want to move from where there's a lot of them to a little of them. So in phase 0, we have calciums entering the cell. And that's depolarization. That's when the pacemaker actually fires. Okay, so now in our next step, we're actually moving to 3. So we go from phase 4 to phase 0 to phase 3. And now we have a cell that has sodium and calcium inside it. And in phase 3, these calcium channels close. So I'm going to put a red X over that calcium channel. It has closed, but another channel has opened up, and I'm going to put it in yellow. And this is our potassium channel. So potassium channel opens. Potassium is very motivated to leave the cell because notice potassium has a positive charge. And the inside of the cell is now positive, so it's very motivated to leave. So in phase 3, we have potassium leaving the cell. And this is repolarization. So phase 3, repolarization. And I always remember repolarization is rest or reset. Phase 0 was depolarization. That's when the pacemaker cell actually fired. After it fires, it has to rest. So it goes to repolarization when the potassiums leave. Okay, so now in most textbooks, what you would see is some kind of line or something like that that would take you from phase 3 back to phase 4, and it would indicate, okay, the cell is now reset and it's ready to depolarize again. But you'll notice in phase 3, we still have a cell full of sodium and full of calcium. So you may be wondering, how does it get back to the state where sodium is even motivated to enter it again? Doesn't make any sense with what we know about electrical gradients. Well, I actually split step number 3 into, or phase number 3 into 2 different steps. So we'll call this step 1 of phase 3, and we'll call this last picture of the cell step 2 of phase number 3. And here is where the sodium potassium ATPase pump comes in. And it's also where something called the sodium calcium exchanger comes in. So in step 1 of phase 3, we had a cell full of sodium. In step 2, The sodium potassium ATPase pump actually pumps out that sodium using energy. So 3 sodiums go out in exchange for 2 potassiums coming in. The sodium-calcium exchanger kicks in because it actually lets calcium come back out of the cell. And it does exchange it for sodium, but remember, a lot of sodium is being pumped out with this ATPase pump. So net, we have sodium leaving and calcium leaving. And that's what happens in step 2 of phase number 3. The other place that calcium can go is inside of cells. There's a little container for calcium. So I'll just put this, zoom in on that cell, and it's called the sarcoplasmic reticulum. It's a little holder for calcium. So calcium can go back into that little container as well. So calcium is inside the cell, but it's kind of hidden in the sarcoplasmic reticulum. And now after that step 2 of phase number 3 happens, we have a cell in which potassium is motivated to enter again. And we go back to phase number 4. So even though I have 4 steps drawn out here for pacemakers, there are 3 steps to the pacemaker action potential. I just drew out 4 cells so that I could clearly show you how the cell actually gets back to stage 4, how it actually resets. Step 1 of phase number 3 and step 2 of phase number 3. So that's ions moving in and out of pacemakers. And one thing that I just want you to notice and think about, that any drug or substance that we give somebody that speeds up sodium entry, which is phase 4, or speeds up calcium entry, is going to increase heart rate, because phase 4 is how the action potential starts. So if you speed that up, you are getting faster to phase 0, which is when the pacemaker actually fires. So I just wanted to point that out, because when we get to the anti-dysrhythmics, you'll be able to better understand if you slow down these steps. Okay, we may actually be able to slow down heart rate or change how these cells are firing. Now let's go to the myocytes. Our pacemaker cells had 3 steps to the action potential, but our myocytes have technically 5 steps to the action potential. So I need to draw one more version of the cell here at the end. So we're going to start at phase 4 and then go to 0, 1, 2, 3. So this is a myocyte. It's not generating electricity. It's waiting for electricity to come to it. So it's waiting for an impulse so that it knows to fire. So in phase 4, it's just sitting there. And the inside of the cell is negative. So I'll put that above the cell. The inside of the cell is negative. Okay, once an impulse hits this negative cell, sodium channels open. So now I'm at phase 0, sodium channels. And sodium absolutely rushes in. They're actually called fast sodium channels, and they rush inside the cell. And because of all that sodium coming in, the inside of the cell actually becomes positive now. So I'll write that above, positive, whereas in phase 4, it was still negative. In phase 0, all that sodium is making the inside of the cell positive. In phase 1, we still have those sodiums inside the cell, all those positive charges inside the cell, in a cell that is positive. That means that potassium is very motivated to leave, because potassium has a positive charge, and the inside of this cell is positive, and there's so many sodiums that potassium is motivated to leave. Now, the potassium leaving doesn't make the cell negative, it just makes it a little bit less positive. So I'm going to write positive over top of this cell again. So it's still positive inside the cell. The potassium leaving has made it a little bit less positive, but it's still positive inside. Now in step number 2 is when calcium channels open. and calcium rushes in. And this is what actually causes the muscle squeeze. Here's the calcium rushing in. And remember, we still have all those sodiums inside too. And now because we are so positive on the inside, the potassiums are even more motivated to leave. So lots of potassiums leaving the cell. The cell stays positive for a little while. As you can see, it's positive in both phase 1 and phase 2 and phase 0. So it definitely stays positive for a while. It depolarized all the way back in phase 0, and then it stayed depolarized in phase 1 and stayed depolarized in phase 2. And phase 2 is when muscle contraction happens. Okay, now we're on phase number 3. So in phase number 3, I'm going to draw the calcium channels again, and I'm going to put a red X through them because the calcium channels close. And we have a cell that still has sodiums inside and still has calciums inside and still has potassiums leaking out. Well, here's where the sodium potassium ATPase pump kicks in again. So I'm just going to call it the ATPase pump, and also where the sodium calcium exchanger kicks in again, just like I explained with the pacemaker cells. So sodium is going to come out of the cell through the work of ATP, I should say. And calcium is going to leave the cell through that exchanger, or it's going to hide inside the sarcoplasmic reticulum, which is like a little bag of calcium in the cell. And the cell is slowly but surely becoming negative again. So I'm going to draw negative over top of step 3. And now we are ready to go back to our resting potential, phase 4. Let's review what we've learned here today. There's 2 kinds of cells that we are worried about when we talk about anti-dysrhythmics: pacemaker cells and cardiac myocytes. They each have a slightly different action potential, which is the movement of ions that causes electricity. And as you will come to learn in future videos, if we manipulate these ions, we can manipulate electricity in the heart. And the movement of electricity, pacemaker cells have 3 phases. I should actually make this more exact. Underneath pacemakers, I have 3 steps written out, but it's actually 3 phases. So I just want to make that word more exact. 3 phases. And for learning purposes, I divided phase number 3 into step 1 and step 2, so I could really show you the action of the sodium and potassium ATPase pump in the sodium calcium exchanger. The other thing that I'm going to add to my pacemaker diagram here is when the cell is positive on the inside and when it is negative on the inside. So phase number 4 for my pacemaker cells, it starts out as negative. Phase 0, it becomes positive on the inside. And then phase 3, it's negative on the inside again. So I'm drawing negative over both step 1 and step 2 of phase 3. Myocytes carry electricity. They don't generate it. Well, they're not supposed to. And so when they carry electricity, their action potential is a little bit different than the pacemakers. There's actually 5 phases to this action potential. We have fast sodium channels, we have the leakage of potassium, calcium channels opening, which is when muscle contraction happens. And then again, just like with the pacemakers, we have the ATPase pump and the sodium calcium exchanger helping to bring everything back to baseline. I could have split phase number 3 into step 1 and step 2 in the myocytes, but I think it was clear that that's where the ATPase pump and the exchanger kick in. Final thing that we have to understand our anti-dysrhythmics is, where do these cells actually live? So here's the heart. Of course, we have the atrium and the ventricles. We have the SA node up here, and we have the AV node down here. So the myocytes, as the name implies, myocytes live in the muscle. These are the contracting cells. They are throughout the myocardium. So here's the muscle layer of the heart. That's where they are. They're throughout the myocardium and the atrium and the ventricles. And they generate force. They pump blood. Now, the pacemaker cells, as you may have guessed, actually live in the SA node and the AV node, which is between the atrium and the ventricles, and also in the His-Purkinje system. And the bundle of His is actually right around here, right underneath the AV node, and then it turns into the Purkinje system, which travels up through the ventricles. So what I have written in black are where pacemaker cells live, and what I have written in red are where myocytes live. In my next videos, I'm going to take you through the different classes of anti-dysrhythmics and how they disrupt these movements of ions and therefore can disrupt dysrhythmias.